Thanks so much, Jess, and I'm very pleased to see so many participants joining. This is a bigger event than I imagined, which is great, of course. Maybe it's partly linked to my slightly provocative title. The title of this talk, Sibling Comparison Designs, Are They Worth the Effort?, was actually also a title of a short commentary I wrote for the American Journal of Epidemiology several years ago. Clearly, I'm pleased with it since I'm using it again. But I think this title really captures a question that I've been struggling with myself for more than a decade now. So let's get into it. Sibling comparison designs. This is not a new idea. The idea of comparing an affected sibling to their non-affected sibling with regards to some exposures or to better understand a phenomena is something I think people have invented over and over again. Many different people may be credited with having this idea. And one of the earlier examples that I'm aware of and that I've read is this one. Healey and Broner, who published a book called New Light on Delinquency and Its Treatment in 1936. And this book summarized their work for over a decade before that. So they had already been working with this for a long time when this saw print. And the main thing they did was to compare 105 delinquents to their non-delinquent siblings. And 8 of these sibling pairs were actually twins, and they got some special treatment in their analysis. And they presented their results in tables like this one. So each, the 2 columns, one is the delinquent sibling and the other is the control sibling. And then it's these are actually numbers, they are not proportions, of these pairs who had much worry during pregnancy or a very sickly pregnancy, etc. So they explored many different possible putative causes of becoming delinquent and drew a lot of conclusions based on when they saw something more frequently in the delinquent sibling than in the controlled sibling. And they, of course, realized that this was a special design compared to not having siblings, and that there was a big bonus in this, that they are similar in so many ways, but not all, blah, blah, blah. Now, this is a fantastic example. Research back in 1936 was a bit different than today. Partly, I mean, they never really used statistics. There are no p-values. Like I said, these are numbers, not proportions. And they really dig into the details. So for these 8 twin pairs, you get a full narrative like this. You get to know the story of these 2 individuals with the interpretation by the authors of like what could possibly explain why one of these twins became delinquent and the other not. And they didn't even stop there. They went full on psychoanalysis and really took it upon themselves to understand the fundamental psychology of these individuals. I'm not going to read out everything that's on the slide right now, but this rampant homosexual, well, yeah, I'll just leave it to Healey and Broner. And but I do highly recommend going back to the archive sometimes to learn from earlier research. So I came into contact with Healey and Broner and sibling comparison designs when I was working on my PhD thesis, which was published more than a decade ago. So I was working on violent crime, psychiatric epidemiology, and we were doing heritability studies where we were comparing the risks in different types of relatives. And I was wondering, like, what else can we do with this material? We have a very rich material of people who are related to each other with regards to crime. And when I stumbled upon this study design, some of the other researchers in the department I was at was using sibling comparison designs, I was just blown away. I thought it was the most brilliant thing ever to get closer to causal inference by comparing related individuals. And I was not alone. At that time, people were writing things like this. From this, the abstract of this commentary paper, the authors said that we argue that the study of twin pairs discordant on exposure, and in particular discordant monozygotic twins, provides a useful analog to the idealized counterfactual design. And this was certainly the impression I got as well. Maybe we can't do random experiments on things like crime, but these twins, they're like an experiment of nature. Because of course, we were very much aware, and everyone attending the CAUSALab series will also be aware, that correlation does not imply causation. And we use this counterfactual definition of causality, thinking like, would the outcome have been different had the exposure been different? The idealized counterfactual design that we cannot do would mean that we have the same person at the same time, but with different exposures, and then we would see if the outcomes would be different. And a lot of the work we do in epidemiology is trying to mimic, get closer to this idealized counterfactual design by restrictions, stratifications, regression models, propensity score methods, and matching. The idea behind the sibling comparison design is a bit like thinking of matching as reaching closer and closer to a quasi-experiment. If matching on age and sex is a good way of removing the confounding from those factors, what if we could match on everything? Everything except exposure and outcome. That would be the idealized counterfactual design. The problem being, of course, that we can only match on things we have actually measured, and that it's very difficult to find these perfect matches. And that's where the siblings enter the picture, especially twins. They would be perfect matches on every factor that is shared by siblings, whether we have measured them or not. I mean, we don't even need to suspect that they are confounders. They would be taken care of anyway. And when we plan a study on this, we could either see it as a case control design, where we pick sibling pairs discordant in outcome, and then we compare their exposures. That's what Healey and Broner did. They compared all kinds of exposures in these delinquent, non-delinquent pairs. Or we could think of it as a forward-looking cohort study. So we pick sibling pairs discordant in exposure and then follow them over time and see what happens with regards to some outcome or many different outcomes. This estimate that we would get from doing this matched study, it must be free from confounding by factors shared by siblings, because they have the same level on all those variables. And many such things are notoriously difficult to measure or model. Things like effects of parenting, socioeconomic status, the combined effects of many alleles, race, all of these things. And again, the big benefit, we don't even need to know about them. They would be taken care of anyway. So one problem is that it may not be easy to get a hold of relatives, but I was working with Swedish registry data. And among Swedish national registers, there is one specifically devoted to relatedness, the multi-generation register. And there's also a twin register with a very high coverage and a lot of interesting data collected on those twins. So with access to these resources, it's possible to do sibling comparison designs of almost anything you can imagine doing with other register-based methods in Sweden. So I was really building up a lot of enthusiasm back in 2011 or something, and I was coming across often this interpretation of co-twin control studies, that you could not only get this estimate that is free from factors shared by siblings, but you could explore what is the confounding by comparing different types of relatives like identical and fraternal twins and unrelated controls. You could look for patterns and like when would an effect go away, and depending on when it went away, was it when you moved from unrelated individuals to dizygotic fraternal twins, or did it go away when you moved further into monozygotic identical twins? This would tell you something about whether it was their shared upbringing or whether it was the shared genetics. What was this confounder that could explain your association? I was very enthusiastic. And then I started actually running some analyses, and I realized I'm not quite familiar with the statistics involved here. I need to do some simulation study to better understand this issue. And I got very surprised when I saw the results of my own simulation studies. Of course, I assumed I had done something wrong. I went back and forth many, many times. But in the end, I felt very confident in saying that this is simplified, it's vague, and it's at least partly wrong. Because siblings are not like other matched controls. Matched controls are sampled at random, conditional on a few matching factors. But siblings are definitely not sampled at random. They are picked from the same family. And siblings, they tend to be similar on all things, Yet a sibling comparison design depends on excluding those sibling pairs who do have the same outcome or exposure. And this is a very strong selection. And as it turns out, it has lots of consequences for the effect measures. So this ended up being a study that was included in my thesis. And a lot of what I'm going to say in this talk is actually from this paper. I still stand by it more than a decade later, but we've also added some analyses and explored this further in various directions since then. So in the rest of this talk, I will give you a very, very brief overview of how to perform a sibling comparison analysis. And I will dig into this, like why this intuitive interpretation is wrong. And I will end with a few tentative recommendations for use. Starting with these statistics, and I'm not going to go into much detail here, a common way of analyzing co-twin control studies back in the day, at least, was to focus on dichotomous exposure and outcomes. And then you would either select sibling pairs discordant in exposure or outcome and compare with regards to the other thing. But it turns out with that design, only the doubly discordant pairs will influence the effect estimate you get. So it doesn't really matter if you see this as a case control or a cohort study, you will end up with the same result. Only the discordant pairs will influence your effect estimate. This was historically often analyzed with McNemar's test. More general models, what is being used today is either using so-called fixed effect model, where you somehow condition away the family. So this can be done in conditional logistic regression or stratified Cox regression, where the stratum is the family. You can also use the between-within models, where you can use a generalized linear model framework. And this is very flexible for different types of outcomes and exposure. But these coincide with that old-fashioned model used for dichotomous exposures and outcomes. And the same idea still holds true. The discordant pairs are the only pairs that will contribute to effect estimates. And when you're dealing with continuous exposures or outcomes, the more different the pairs are, the more influential they will be in the effect estimation. The between-within models are, as I said, a simple extension of a generalized linear model. So if a generalized linear model is written like this, many of you will recognize the link function G around some expected value of an outcome conditional on some exposure. The difference from a standard model to a between-within model is that you include the pair, the sibling mean in these exposure variables as covariates in the model. And because you can use different link functions, this can be a linear or a logistic or a probit or a Poisson or any other regression model that fits in the generalized linear model framework. In an ordinary generalized linear model, you get an intercept and you get the effect or the measure of an association, the regression coefficient beta. When you include the pair mean, you get a within pair effect, W for within, and you also get that weird number that is the between coefficient. Some authors have tried to interpret this in various ways, and of course there is some information in it, but generally speaking, I wouldn't recommend trying to interpret it. It is a weird number. It says something about the distribution of variance between and within pairs, but really what you're after is that within pair effect. You can state the between-within model in different ways. I prefer the versions that I stated before here, where you have the exposure and you have the pair mean in exposure. But you can also model instead the deviation from the mean. You will get the same within pair coefficient if you do that. So I'm only mentioning that for completeness. The thing with the between-within model is that it becomes tedious with many covariates, because everything you want to add and adjust for, you should also center on the family. You should include the family means as well. Otherwise, you haven't adjusted those for the family. So quickly, this becomes tedious to program unless you have someone else's program to do this, which is a good argument to stick to like conditional logistic regression, etc., if it's possible with the study design you have. There are many other terms you may come across: co-twin control study, discordant twin designs, etc. But essentially, they all provide the same within pair estimate. Of course, there are some designs that are just flawed and incorrect, but most of the time, people are doing variants of this, and they produce the same type of within pair estimate. And this within pair estimate, when the confounding is perfectly shared by the pair, and there is no other bias, then this within pair estimate will indeed be an unbiased estimate of the causal effect. This is true, and it's a great benefit of these designs. So then what's the problem? Well, like I said, the problem is the selection. Siblings tend to be similar, correlated on most things. Certainly confounders, but also on the exposure and the outcome. But the sibling comparison design will only use sibling pairs that differ in exposure. This means that we are selecting pairs that differ in exposure, despite the fact that siblings overall tend to be similar on exposure. We are thus oversampling pairs that differs in factors that can make siblings different in exposure. So when you compare the exposed and the unexposed in your sibling comparison, they will be more different on these factors than if you were to compare exposed and unexposed in the complete sample. And that means that any confounding by those factors will be increased in the sibling comparison. In the past, I have tried to explain this using directed acyclic graphs, but I'm not going to try to do that today because I don't think DAGs are very good for these kind of reasonings. This is a question about the effect size. DAGs care about whether there are associations and conditional independencies. So I think they're more confusing than helpful in this case. But if you want some DAGs, you can check out some of the references that I mentioned throughout this talk. Instead, I'm going to jump into this major issue, the amplified confounding, where the problem really is the effect size. And I think it's easiest to understand this looking at the math. This is an equation for a simple linear regression coefficient. It is the ratio of the covariance of exposure and outcome divided by the variance in exposure. By restricting to sibling pairs, we are reducing variance and covariance because there is less variance and covariance within sibling pairs than in the full population. We keep only the within pair variance in exposure, and we also reduce the covariance. By how much? Well, that depends on why this covariance exists to begin with. If the association is completely causal, then the covariance is there because of the variance in exposure. So it's actually reduced by the same proportion as the variance in exposure. And that means that this ratio is the same. So when the regression coefficient is there because it's a completely causal effect, it will be the same within pair as in the whole population. If the association is completely due to confounders shared by the pair, then the covariance will go away completely. Within pairs, there is no longer any covariance, and then this regression coefficient will be 0. But what if the association is due to confounders that is not perfectly shared by the pair? Then this ratio will change, and the amount it will change will depend on whether the exposure or this confounder is more strongly shared by siblings. Before I show you equations to support this, I'll just mention that this is a special case of what is called bias amplification, which is a known phenomena. Many who work with propensity scores, they have been taught this in basic classes, that you should never include instrumental variables in a propensity score model. The reason why you should not is that that will actually increase confounding by other factors that you may not include in this propensity score. It can also influence the standard errors quite a bit. If you want to read more about bias amplification, you can check out these two references. And the take-home message is that if you adjust for factors that are associated with the exposure, this will increase confounding from factors you have not adjusted away. This is always true. It's often overlooked in our studies. The sibling comparison design sort of does this. And I'm not going to go through the proof of this. You can follow up on the reference. But under a linear model where all the effects could be described by a linear regression, then we can derive mathematically what the confounded regression coefficient is. And you can see here that what we observe, so it's confounded, the regression coefficient beta is a sum of the causal effect beta yx and this term, which is a ratio depending on the strength of the confounder's association to exposure and outcome. If we go within pair, the equation changes to this. It's a quite similar expression, but the difference is down here. So there's a ratio here inside the ratio. And this is a ratio of 1 minus the sibling correlation in exposure and 1 minus the sibling correlation in confounder. So the conclusions, the take-home things, is that when the sibling correlation in confounder is 1, so all confounding is shared in sibling pairs, then that thing becomes 1 minus 1, 0, it's divided by 0. So this whole extra term goes away. The only thing that is in the beta W is the beta yx. So we actually get to the causal effect. Splendid. But when the correlation in confounder is the same as the correlation in exposure among siblings, then actually the within pair estimate will be the same as the cohort estimate. So it will be equally confounded. We're not removing any confounding in that scenario. And when the sibling correlation in confounder is less than the sibling correlation in exposure, then the within pair estimate will actually be more confounded than the ordinary estimate we get in the population. This can also be shown in simulations. So here's simulations under a logistic model, and we want to find an odds ratio of 5 because that's the non-confounded estimate. But we are seeing a confounded odds ratio of 8. And now in different scenarios where we alter the correlation in exposure and confounder in sibling pairs, we see that the within pair odds ratio changes. Of course, the population odds ratio stays the same. In the population, it doesn't matter what the correlation among siblings and exposure is. So the confounded odds ratio is always 8. But in a few scenarios, when the correlation of confounder in sibling pairs is 1, we get to the causal effect. Otherwise, we are here either decreasing or increasing the confounding, depending on which is stronger, the sibling correlation in confounder or the sibling correlation in exposure. Now, this is not all. The selection also means we are amplifying measurement error. And I can give you one intuitive explanation for why this is. If we imagine that we have an X star, which is our measure of the exposure, then this could contain noise from factors that are not associated to the outcome. And this is what we would call non-differential misclassification. So it's random with respect to the outcome measurement error. Now, say that our exposure is almost perfectly shared by siblings, very strong sibling correlation, but there is a substantial random measurement error. Now, we do a study here where the design selects sibling pairs that are discordant in measured exposure, X star. Why are these pairs different? Well, if you follow that sentence I just said, the most likely explanation is actually measurement error, because most of the time siblings have exactly the same exposure. So then we have actually increased the noise in X quite a bit when we go within pair than before. This can also be shown mathematically. So here are the equations you end up with if you go through all the math. The second equation is the regression coefficient we see under random measurement error. It's just the reliability of the measure times the causal effect. So ordinarily, random measurement error will dilute the effect estimate we get. We will underestimate the causal effects. The equation is much trickier in this within pair coefficient. But if you dwell on these equations for a little while, you will accept that the within pair estimate is always more attenuated than the effect estimate in the full population. And how much more attenuated it will be depends on how strongly the exposure is correlated in siblings. And this is still a simplified equation. If you add confounders to the mix, you get a more complex equation, but the same idea still holds. And we can show that again with a simulation. So like before, we want to find an odds ratio of 5 because that's the causal effect. And this time there is no confounding. So on the top line, when we have a measure of the exposure with perfect sensitivity and specificity, we do find this, this causal effect, both in the standard odds ratio and in this within pair odds ratio. But then you can see both are attenuated when we start to add measurement error, but the within pair odds ratio is more attenuated than the estimate in the population. And this is not all. A sibling comparison design will also suffer bias from cross-sibling interactions. And what is this? Well, the math underneath a sibling comparison design, it assumes that there is no causal effect of one sibling on another sibling, that they are independent, even if they belong to the same family. So what if that's not true? What if there is an effect between these siblings? And one example, which is based on a true study, is imagine that we want to do a study of interpregnancy interval and the risk of late miscarriage. So we suspect that going a shorter versus longer time between your pregnancies could influence the risk you have of having a late miscarriage. So here's an individual that had 3 pregnancies, and that means that we could do a sibling comparison here, where the siblings are the children being born, or like the fetuses that could potentially have been born. And we would then have 2 intervals, so we could compare the risk in this second pregnancy and the risk in the third pregnancy, where this interval 1 and interval 2 are the exposures for these pregnancies. But what if women with a late miscarriage wait longer before having their next child than women without a miscarriage, so that the outcome of one of these siblings influence the exposure for the next one? Well, in that case, since we only select women who are discordant with regards to miscarriage, in our sample where in one pregnancy they did have a late miscarriage, in another they did not, we will have, through the selection, made it so that longer intervals are associated with not having a late miscarriage, because they had a miscarriage already in the first one, and that meant that the exposure for the next one was a longer delay. So this is very problematic, very problematic. And it means that just in our sibling comparison design, we will create new associations from this cross-sibling effect. And these can be very strong if you put numbers on it. So this can easily override other like causal effects and biases. If you want to dig into this more, we wrote a paper on it, me and Arvid Sjölander and some co-authors. And the take-home message is that there's no problem if it's the exposure of one sibling influences the exposure of another sibling. And if the problem is an exposure of the first sibling influences an outcome of the second sibling, this is not without problems, but it can be managed. But when it's the outcome of one having an influence on either the exposure or the outcome of the others, then that is a big, big problem. But there are some good news. You can actually assess this in the data you have. You can compare with the late miscarriage story, for instance. You can compare, you know which is the first and the second pregnancy, and you can look for asymmetries in waiting times and whether it matters if the pregnancy where there was a late miscarriage was the first one or the second one. Do you get different results? So there's at least something you can do with the observed data with regards to this problem. We're not done yet. There are more problems with the sibling comparison design. Reduced generalizability. Now, this is something that has been brought up quite a bit with regards to twins. And the question is this: are these discordant pairs representative of the population? And the answer to that is clearly a no. If they were completely representative of the population, we wouldn't be able to get rid of confounding by looking within them, but we can. So that's not really the question. But the question is more this, like, are people with siblings different from those without? And are these discordant sibling pairs, do they have the same or different distribution in other variables that may be effect modifiers? So this can change what is the target population. Like, should I actually expect that the estimate I see in discordant pairs applies to the full population, or is this population somehow different? With regards to twins, this has been brought up many times to critique co-twin control studies, especially of perinatal exposures, where the claim is that a twin pregnancy is just very different from a non-twin pregnancy, and maybe we cannot conclude, based on what we see among twins, something about more ordinary pregnancies. And this has been discussed a bit back and forth in the literature. I think some of the key evidence that twins still probably are pretty generalizable are from studies like this one, which look at like twins overall. Is there a difference? Are twins different with regards to mortality or morbidity compared to non-twin individuals? And the answer is overall not really. Even though it's very common that one twin is a bit growth restricted compared to the other, there's some catch-up growth to be had. So on average, it's not that twins are much unhealthier than non-twins based on their perinatal circumstances. But this can certainly be discussed, and it may depend on the specific question you're asking, whether this is an issue or not. With regards to the distribution of effect modifiers, you can argue that under many plausible scenarios, the selection of discordant pairs, which is built in, even if you don't do it yourself, the analysis will enforce this on your data. It's likely that the population that is discordant may differ in some factors. Difficult to come with a theoretical statement in general, but you can, of course, look into this in your data. Do the discordant pairs differ with regards to some factors? One of the arguments for why you may expect to find differences is that for instance, if it's income, that's the exposure you're interested in, so childhood income. Well, maybe childhood income discordant siblings more often come from high-income families. Maybe the variance in income between siblings is higher in the high income versus the low income part of the spectrum. And if so, other factors that are associated with high income may be more common in these income discordant sibling pairs. And if those factors are effect modifiers, then you should expect to find a slightly different or very different effect estimate compared to the full population. This raises further questions, like are we estimating conditional or marginal effects? What is the target population in a sibling comparison design? And this is discussed a bit more in this paper. But I'm going to say that I'm not super worried about this point. I think a lot of this discussion about conditional versus marginal effects is a bit academic, if I'm being very bold and general here. Even if it's true that effect modifiers are likely to be a bit different, most of the time it's not the fact that these completely inverse an association or something. It could just be that the estimates are, if it's 2.4 or it's 2.2, does that actually matter so much for our conclusions? But that's my personal view on this. But I'm going to summarize this problem aspect with this. The selection of discordant pairs will, good thing, remove all confounding by perfectly shared factors. Bad thing. No, okay, so this was not a good thing. Sorry, I'm not reading my own bullets this time. It would also reduce confounding by factors more shared than the exposure. But the bad thing is that it will amplify confounding by factors that are less shared than the exposure among siblings. It will also increase attenuation from random measurement error. It could possibly introduce bias due to sibling interactions, and it could raise questions about the generalizability. So that's not great, maybe. Sibling comparison designs may thus both increase and decreased bias compared to the unpaired cohort estimates. And some of these, what I said in the beginning, some of these like recommendations for interpretation that were out there in the literature, when I started reading up on these studies more than 10 years ago, they're simply wrong. Because even if an association remains unchanged when you do a sibling or twin comparison, it can be substantially confounded by factors influenced by genetics and the family environment. Genetics are, after all, correlated 0.5 in siblings, in fraternal twins and other siblings. And many exposures may also be correlated 0.5. So you should not, generally speaking, expect the sibling comparison design to remove confounding by genetic factors. It's also the case that an association can completely disappear, at least in terms of statistical significance, when you look inside the pair, and it can still be completely causal, because it's possible that it's all an attenuation due to measurement error. So some important quantities in a sibling comparison is the reliability of the exposure measurement, how much measurement error is there, the correlation in exposure, and if you're using different types of relatives, then you need to consider this correlation for the different types of relatives. And you should also really be worried about the degree that one sibling's outcome could influence the other sibling. Now, I've worked on this from the perspective of sibling comparison designs, but the math doesn't know that we are looking at siblings. So all of this applies completely equally to other within cluster analysis, like the case crossover design. I don't think that's always recognized. So this all sounds very bad. So let me moderate that a little bit. It's true that sibling comparisons can amplify confounding, but we can try to adjust for this confounding. I mean, confounding is an issue, whether you use sibling comparisons or not. It can amplify measurement error, but we can actually try to account for different degrees of errors by doing some sensitivity analysis, for instance, where there is math here to back this up. It can introduce bias from cross-sibling interactions, but we can check for asymmetries in the data that would indicate such interactions. So there's at least something we can do to investigate that. And personally, I'm not super worried about the reduction in generalizability. What I am worried about in practice, and what to me really limits the use and utility of these designs, is that the low power is a major issue here. In the commentary I wrote, that commentary was sparked by these two papers, where the two different research teams were looking into the possible causal effect of maternal smoking during pregnancy on autism spectrum disorder in the offspring. And these two studies, they had rather similar results, really. If you look at the one estimated hazard ratios, the other odds ratios. But you can see in the first study, the Danish study, there was an adjusted for various potential confounders, but still significant hazard ratio of 1.17. Within sibling pairs, there was no association. In the other study, there was an odds ratio of 1.15 after trying to adjust for some possible confounders. And within siblings, it's also not really an association, but the confidence intervals are so wide that it's very difficult to say something. Both of these studies were based on fairly large populations, so it was very difficult beforehand to tell whether there was sufficient power or not to do the study. You really had to do the study before you could conclude whether the power was sufficient or not. And it can be discussed, of course, like the first study, the Danish study, it concluded that the sibling comparison design is a strong argument against a causal effect. But if you look at the upper end of the confidence interval, this is, in my experience, often the case. The low power, when you focus on this discordant pairs, means that it's difficult to say whether the effect estimate, is it lower, is it the same? Are we really confident that this is a null finding, or is it just because of low power that it's no longer significant? So I'm gonna end this talk and leave time for questions with my own tentative recommendations. I think sibling comparisons are most useful when you honestly suspect that there is a completely shared factor, like childhood socioeconomic status, that could explain the whole association. So you're after the scenario where you find an association in the population, you do a sibling comparison design, and there's a null association that you are powered well enough to be confident that this is a null finding. I think that's, if that's what you see, it's a fairly compelling argument, I think. The problem is that you often end up with a more wishy-washy within pair estimate, which maybe is higher, maybe is lower, but that is difficult to interpret due to the many, many factors that make this within pair estimate a bit numerically different compared to the cohort estimate. I also think that you should definitely adjust for sibling comparison designs for all the confounders you can imagine, and you should be particularly aware of confounders that could change within siblings. If you're comparing different pregnancies within a woman, you can consider like what other things change within a woman between pregnancies that may be affecting these things. Even factors that in the population are fairly rare, not a big confounder, they could be important for these within pair estimates if they are the explanations for why a woman would change her behavior. Why did she stop smoking between pregnancies? Why did she start smoking between pregnancies? Those factors could be strong confounders of the within pair estimate, despite the fact that they may be negligible in the full population. You should also consider getting some measure or some idea of the measurement error in exposure. And it's very possible to perform a quantitative bias analysis of this if you want. And you really shouldn't use sibling comparison designs when the outcome of one sibling influences the exposure of the outcome of the second. You can investigate the data to try to see if this maybe is a process that could occur. But if you conclude that, yes, there's a risk that this is there, I'm not aware of any solution to that with the sibling comparison design. You're just screwed. Finally, I really, really want to emphasize that you need well-powered studies to separate the different possible explanations. So it's not really worth doing a sibling comparison design in a very small material. That's my view. So with that, I want to thank you for your attention and end with a few last references. The commentary that I'm reusing the title for, and also a review paper that Arvid Sjölander, Sara Öberg, and me wrote recently about the statistics mostly, so more on the math side of these, the methods used for sibling comparison designs. So with that, I just say thank you, and we have time for questions.